We are back to section 4.3 and the first derivative test. What is first derivative test? First derivative test for local extrema. Suppose that c is a critical number of a continuous function f. If f prime changes from positive to negative at c, then f has a local maximum. So f prime, this is f prime, and f prime is positive before c, and after c it's negative. What does f do? F is going to be increasing, then decreasing according to the theorem we just proved, and therefore there is a local maximum here. And the second part is saying is f prime is negative before and then changes to positive. This is f prime, so f is negative, then it becomes positive. There's a local min. And then if f prime does not change sign at c, then f is neither a local max or local min. And if you see this, if f prime doesn't change sign, then if it's increasing, it's going to stay increasing. If f is decreasing, it's going to stay decreasing. And here's one in that situation. F prime is positive before, f prime is positive after, therefore there is no local min or max. Here is f prime is positive, then becomes negative, negative, then becomes positive, and so on and so forth. Now let's do an example. Example 5. Find the extrema of f if you know, notice, f is not given, but f prime is. So let's use the first derivative test to find the local extremas. Now, this example 5, find the local extrema of f if f prime of x is equal to x minus 4 to the power 3 times x plus 3 to the power 7, x minus 2 to the power 6. Notice that the problem is giving you f prime, so you don't have to calculate f prime, and it saves you a little bit of time. And so now in here, I'm looking at this function, and I see, I'm trying to figure out what the sign of f prime is, because sign of f prime will tell me, is going to help me with the first derivative test. Sign of f prime, again, by intermediate value theorem, I have to find all the points of discontinuity and all the zeros. Here is only points of only zeros, no points of discontinuity. 4 is a root, negative 3 is a root, and 2 is a root. Negative 3, then 2, and then 4. Now, if you notice, in here, if I plug in this value, f prime, as x goes to negative infinity, very big number, negative number, minus 4 to the power 3 is very big negative number. Very big negative number plus 3 to the power 7 is still very big negative number, times very big negative number to the power 6, which is going to be a positive number. So negative times positive, this is positive toward the negative infinity. Also, as it goes to positive infinity, very positive number to the power 3, positive number to the power 7, positive number to the power 6. Over here, two end behaviors are positive. And another way of finding this is a polynomial, and the degree of the polynomial is going to be even. Just add up 6 plus 7 plus 3 is going to be an even number. So the end behavior is going to be positive. Now, at every 0, the sign may or may not change. By intermediate theorem, at other places it won't, and since this is continuous everywhere. And so I'm looking at this, and I look at x equal to negative 3. X equal to negative 3 is part of this factor, that's of odd degrees. Therefore, the sign changes as we pass x equal to -3, becomes negative. X equal to 2 is an even degree, so the sign does not change. And x equal to 4 is an odd degree, the sign changes, which already, because of the end behavior, we have it. Now, look at the if f is increasing or decreasing. Increasing here, decreasing here, decreasing here, increasing there. And so over here I see a hill, and here I see a valley. So at x equal to -3, local max. At x equal to 4, local min. And at x equal to 2, neither. Now let's do another problem similar to this. And so this was the first derivative test again. Using the first derivative, the sign, we figured out the local min, local max, and the rest. And now let's do another problem. Problem example 6. Find the local extreme of the function f of x equal to x plus 1 or to power 2 divided by x times x minus 2. Notice this function is not continuous everywhere. Namely, it's not continuous at 0 and at 2. So when you take the derivative, in those points are gonna not be part of the domain. But then the first thing that you do, you have to take the derivative because it's a first derivative test to find the local extreme. So when you take the derivative, remember this is a quotient rule. Do the quotient rule. Remember that you have to factor as much as you can to find all the roots of numerator and denominator. Roots of denominator to find the points of discontinuity of f prime. Roots of numerator to find the zeros of the f prime. So if I put all in and I see I have a -1, that's a 0. Here I have 1/2. Here I have 2, which is not in the domain, then 0. So I put all those points on a number line. And then what I see is that as x goes to -infinity, this part is going to be a positive value. As x goes to very negative value, very large negative values, this part is going to be positive. This part is going to be negative, and the ones in the bottom are to power 2, so they are positive. So toward the -infinity, I have a negative number. Toward the positive infinity is this again. Toward the positive infinity, this part is going to go very big positive number. This one is going to be very big negative number. And here is just positive. So it's going to be positive times negative. So I get a negative number again on this side. Then the same way that we treated the roots, we can treat the roots of the denominator as far as this, if the sign changes or not. X equal to -1, which is the root of the numerator of degree 1, the sign has to change. So from negative we go to positive. At x equal to 0, the degree is even, so the sign doesn't change. At x equal to 0.5, the degree is odd, so the sign changes. At x equal to 2, the degree of x minus 2 is even, so the sign doesn't change. Now, looking at this, I can see this is f prime, so f would look like this: down, up, up, down, down. There's one, and there's a bottom of a hill right here, and top of the, bottom of a valley down here, top of the hill over there. So at x equal to -1, there's a local min, and at x equal to 1/2, there's a local max. And And if you graph the function, you will see from pre-calculus, we sort of knew how the end behaviors are, and we knew how because we could find the limits. Now we know better how to find the limits, and we knew that at x equal to, if we have the denominator has 0 at 0 and 2, we will have two vertical asymptotes right there. Now there's a little bit of more information than I know about increasing, decreasing, and finding this local min over here would not have been possible with the pre-calculus knowledge that we had before. And this local max also was not available to us with the information that we had in pre-calculus. So we're getting more information, and this is going to end up graphing functions like this in the following sections. Now, I click on question number 3. Let f of x be x to the 4th minus 4x to the 3rd plus 2. How many critical numbers does f of x have, and what kinds of extrema are they? And so I suggest to stop the video and then come back and answer the question. So now that you stopped, let's see. I'm in the section that I'm taking the derivative to find to use the first derivative test. So f prime of x, and then I get 4x to the 3rd minus 12x second. And factor to find the critical numbers, I can factor 4x to the power 2, and I get x minus 3. So the values are 0 and 3. Those are the critical numbers. And since this f prime, and I'm finding the sign for f prime, right? Since f prime is a polynomial of degree 3, toward negative infinity is negative, toward positive infinity is positive. At x, x is a root of the exponent of the root is 2, therefore the sign doesn't change at 0, and the exponent of x minus 3 is an even exponent, and so the roots so the sign changes in there. So then that's the multiplicity of the root. Multiplicity of root here is of multiplicity 2, here of multiplicity 1. And so it goes down, down, up. There is a local minimum, but no local maximum. And there are two critical numbers and a local minimum. One, no, that's not it. Two critical points. One is a local min, the other one is neither. And that's the correct answer.